All right, I'm gonna get started. Welcome to lecture 16 of 1413. We talked a lot about utility from beliefs and how, in particular, anticipatory utility, utility about thinking about the future and what might happen in the future may affect people's utility. And then, how that in turn might affect how people, A, choose when to consume or when to engage in certain activities, because anticipatory utility provides some motivation to push things forward at least a little bit so people can look forward to positive events. Second, we talked about information acquisition, about the idea that people, if they derive utility from beliefs, that might affect how much information they might want to acquire. In particular, we talked about the idea that when you think about like potentially negative information that you might receive, in particular, we talked about Huntington's disease when people had like negative health information, that they might not want that information with the motivation that they would like to make themselves feel better about themselves. They might sort of think that they're healthier than they actually are, and they might look forward to like a healthy life at least for a few more years, and that might depress their willingness to gather or receive information. Now, we talked a little bit about then a model and how to think about this. First, we talked about a model where people did not have the choice whether they could manipulate the information themselves. So we just talked about like when somebody wants to seek or reject information, but we had the constraint, we had imposed a constraint. Let me go back for a second. We had a constraint imposed where we said, well, the person needs to be hold correct beliefs conditional on the information that they have been exposed to so far. So essentially, that was just an idea of like, okay, here's some information that the person could gather, but the constraint was this number one that I'm showing you here is that beliefs need to be correct, as in like the person is a Bayesian conditional on the information that they have received so far. And then we sort of said, well, if we think about this, if this is just about like when to gather information, and we considered so far the case where the person could not actually affect future outcomes. So that's the case of like, say, Huntington's disease, where there's no cure, there's nothing you can do about it. The question was just like, would you like to receive some information that's going to happen in the future or not? Then we, and I'm not going to go to this in detail very much, we then looked at the conditions that are involved for when does the person want to know about this. And the condition was essentially about this function of f of p, where f of p was essentially the utility derived from beliefs. And the condition was either if f is concave or f is convex. If f is concave, the person is information averse. If f is convex, the person is information loving and would like to find out about those things. Now then we said, well, consider now also the possibility that people might be able to manipulate their beliefs. Right, so you might sort of say, what are the reasons? Why might you ever want to hold correct beliefs? And then the above framework, if you could choose what your P is, there's really no reason whatsoever to not choose P equals 1. Remember, P here was the probability of your health being good, of being HD, Huntington's disease negative, of not having the disease. So if there's no negative consequences of what's going to happen in the future, surely you have all the incentives in the world to deceive yourself and make yourself think that you are healthy, right? And so now then the question was like, well, and this is what I was showing you here. This is the expression that's here. There's essentially f of 1, and that's larger than f of p for any p that are there. And then if the future, this is the term here, what's actually going to happen in the future, if that's independent of your beliefs, in the sense of like that's going to happen anyway, you might as well make yourself believe that P is large, P is 1, you're healthy. Now, then what we left things at was the question of like, well, why might you not want to choose f of 1 anyway? Or why might you not want to say P equals 1? And that's a question to you.
If your belief of what's going to happen might affect the future outcome in a negative way, you like I guess if there were a treatment available for Huntington's disease, you would rather know whether you have it.
Right. So Huntington's is not the greatest of all examples that I chose to start with because, there's no cure. Um, but you're right. Like, for example, in particular for diseases such as HIV or the like, surely it would be very helpful to know because then you can sort of engage in appropriate treatment that might actually help you get better. Presumably, you only get the treatment if you actually know what the disease is like. In the specific Huntington's disease, we also talked about a few things. We talked about sort of other actions that you might be able to take. For example, if you are able to, save for retirement, if you're able to go to travels before you get sick, or like there was questions about whether people want to have children, questions about like what partners they want to be with, and so on and so forth. So if there's a bunch of sort of other economic choices or other choices in life that depend on whether the person is positive or negative, it seems like that person should want to know. And then sort of deluding yourself might get in the way of making optimal decisions. But broadly speaking, just to summarize, if there is no action item, as in like if there's some information about the future that where really, even if you knew the information, there's nothing you can do about what's going to happen in the future. It's not obvious why you not want to just delude yourself and think like things are rosier, the world is looking better than it actually is, because it might just make you happier, at least in the moment, even if things in the future might turn out to be bad. And so this is what we already just discussed. So incorrect beliefs can lead to mistaken decisions. Well, that's correct, but sort of overly positive beliefs are an economically important implication of utility from beliefs. That is to say, on the one hand, and you might, and this is what we just discussed, you want to believe that you're healthy if it makes you feel better about yourself or the currently or the future. So you might want to convince yourself that that's the case. But this is what we just said, over-optimism distorts decision-making in some ways, for example, health behavior, whether you want to seek treatment, but also whether you want to sort of adjust to potentially bad events in some other ways in economic choices. So you might not want to be like over-optimistic because of those distortions. And then sort of the optimal expectations will then trade off these two things. On the one hand, you're healthier, maybe happier right now, thinking you're healthy. On the other hand, or thinking that the future will be bright anyway. On the other hand, it might make change your choices in some bad way. Now, there was another reason that people mentioned, which was potential for disappointment, right? If you think, the future is always going to be great, even if you can't affect it in any way, well, at some point, reality is going to set in, and then you might get really disappointed. We haven't really talked about this very much. That's a way in which you can think about perhaps people potentially choosing their reference point. So if you think people have like reference-dependent utility, and if you really were optimistic very much in a way that allows you to potentially choose your expectations and your reference point, and then you might not want to be overly optimistic because your reference point might be then too high, and any outcomes that you then eventually receive, you might sort of view worse because you expected really good things to happen. So to the extent that like being too or being overly optimistic leads to disappointment, you might not want to engage in over-optimism, even if there's nothing you can do about the outcomes because of that potential disappointment. But sort of in general, for decision-making with anticipatory utility, at least some over-optimism leads to higher utility than realism, because essentially it makes you feel better in the moment. But there's sort of this trade-off potentially with how good you feel in the moment versus how disappointed you might be in the future in case you're too over-optimistic. Any questions about this? Oh, sorry. Okay, so then let me show you some other optimistic beliefs in addition to the evidence by Emily Ostwald already showed you. So there's a classic sort of study by Weinstein in 1980 that asks students to make judgments of their students' chances for outcomes. It's kind of similar to the question that I'd asked you at the beginning of class. there are two measures that Weinstein uses. One is what's called judgment. This is, excuse me. This is how much more or less likely the average student thinks the event will happen to them relative to the average student. And the second one is what's called the optimistic-pessimistic ratio, the number of students who think their chances are better than the average classmates divided by the number who think their chances are worse. So these are both sort of measures of over-optimism. They measure slightly different things, but they're broadly, they're fairly highly correlated. So what does Weinstein find? Clear sort of evidence of over-optimism when you look at different things about like stuff that's going to happen in your life, owning a house, a salary of larger than $10,000 a year. I think this is, 1980, that's been a while ago. Traveling to Europe, living past age 80 and so on. The comparative judgment is always fairly high, so that number would be 0 if people were on average realistic. Remember, comparative judgment is how much more or less likely the average student thinks the event will happen to them relative to the actual average student. And the optimistic-pessimistic ratio, that should be like a 1 if people were sort of like not over-optimistic. It's also clearly a large N1. Remember, that's the number of students who think their chances are better than the average classmates divided by the number who think their chances are worse. That works for positive events, but also works for negative events. So when you ask people about like drinking problems, suicide, divorce, heart attacks, all sorts of bad things, people think they're now, of course, less likely to happen to them, these kinds of events. And then again, the optimistic-pessimistic ratio, that's positive. That's just because it's like the outcome is flipped. So people are way more optimistic or about, they think they're not going to have drinking problems, get divorced, get heart attacks, and so on. So people tend to be very optimistic about their future lives compared with when you ask them to compare to others. Now, there's other examples of that. Couples believe there's a small chance that their marriage will end. Small business owners think their business is far more likely to succeed than their typical similar business. Smokers understand the health risks of smoking, but don't believe these risks apply specifically to them. There's a long list of these kinds of behaviors. People tend to hold rosy beliefs about their future, even in the presence of like sort of objective information. So even if you give people information about the health risk of smoking, they understand the health risk, but then they're like, well, that's not going to apply to me. Of course, there's no good reason to actually, these risks should apply to anybody. So people just want some things to be true, presumably because it makes them happier in some ways. Oh, excuse me. So then beyond future prospects, people also tend to have overly positive views about their abilities and traits. So for example, 90% of drivers think they're better than the average driver. 94% of professors at the University of Nebraska think they're better teachers than the average professor at the university. I don't know what this number looks like at MIT, but probably it's larger than 50% as well. So there's you can find this kind of evidence from a range of domains. In some cases, there's some other potential explanation for this, but broadly speaking, there's pretty robust evidence that people are overconfident and overly positive about A, what's going to happen to them in the future, and B, about thinking about their own skills and abilities. Now, if you look at MIT students, however, in contrast, when you ask MIT students different questions, and this is from a recent survey from a few years ago that MIT sort of asks students. One question here is academically, I would consider myself above average at MIT. People say about 31% of students say they're above average. In particular, female students tend to think they're below average. People might have biased beliefs about the average. So what you think is an average MIT student might actually be like the 5th or whatever, like some of the highest percentile, because essentially you're exposed to all the success and math Olympics and whatever wins that people receive, which is just not what the average student is like. There's of course also very severe selection in terms of there's so many smart and brilliant people at MIT that in a way sort of people's perception is quite biased. The questions here were asked about the average at MIT, but even there, I think people might sort of just be biased in terms of thinking what's the average. There might also be some worries about disappointment in the sense of, this is what I was saying before, when you think about like being overconfident, maybe in some ways, so one issue with, or one reason why you might not end up being overconfident for a long time is if you receive feedback. And at MIT, people receive lots of exams and so on, where you can sort of learn or interact with others, where you can sort of notice how people are doing overall. And sort of, if you're worried about being disappointed, or you have been disappointed several times already, then sort of thinking like you're the smartest person in class might not be a good idea, because you might get disappointed again. And then we'll talk a little bit more about gender in a different lecture later. That's a very common theme. One second, is that female MIT students, or in general women, but in particular also female MIT students, are particularly underconfident. We don't exactly know why that is, but it's a very robust finding, not just at MIT. In some ways, then there's still a question, so it's a very nice observation that in a way, beliefs can also be a form of self-motivation. So if you sort of are really interested in academic success and being really good at exams and so on and so forth, if you are underconfident, that can be a motivator, and saying like you're really worried about failing, you're really worried about doing badly and so on, then you work extremely hard and then you do better in exams, you surprise yourself positively. That can be sort of an important motivator. Of course, that could also go the other way. It could be really discouraging. If you think you're really terrible at everything, then you might sort of, at the end of the day, you might not study at all anymore, because like, what's the point? So there's a bit of a trade-off here as well. And it could be that if you sort of think that people are, when they're underconfident, that leads to motivation and it makes them better at school, plus they're going to be less disappointed and get like positive surprises, that could be an explanation. I think there's a bit of a question again, why is that the case at MIT and not sort of in the overall population? But it might have to do with like the frequency of feedback and like school and so on and so forth, and maybe also just with social norms or other things that maybe are somewhat trickier to explain. I was teaching Harvard undergrads as a grad student. I'm not so sure that Harvard students are underconfident, to be honest. I haven't seen the survey evidence on that, but my sense is that MIT students are more underconfident compared to Harvard students. Let's leave it at that. But I think it's true, like if you look at Caltech and other type of schools that are very similar to MIT, I think my guess is you'll find similar results in those kinds of surveys. Okay, so the next thing we talked about is very quickly is what's called ego utility. So far we only talked about anticipatory utility, which was the idea that people want to look forward to good things in life, and therefore they're sort of have inflated beliefs about what's going to happen in the future. A very related aspect is what's called ego utility, which is, so just to recap, inflated beliefs might be explained by anticipatory utility, essentially to say higher ability means better future prospects, and people want to convince themselves that they have high ability, and therefore, if you think you're really smart, that means like good things going to happen in the future. But it might also just be like right now, you're just feeling better about yourself, and therefore you have like inflated beliefs about yourself. So that's often like tricky to distinguish empirically, in the sense of like, I might just feel like I'm good looking, smart, and so on and so forth, because it makes me feel good right now, or I might want to hold those beliefs because that means like good things is going to happen in the future, and I will have a bright future going forward. So these things are slightly tricky to disentangle, and both of them probably play an important role at the end of the day. So yeah. Now, one thing I'm going to talk about a little bit more also later in the semester is about mental health. And so there is this literature that sort of argues that positive illusions are promote, in fact, psychological well-being. So that's sort of the argument that is here, that overconfident is in fact vital or important for maintaining mental health. So, overconfident, that makes people like happier. It's people are better able to care for others if they think they themselves are doing better. They're better at doing creative and productive work. That's also better. Overconfident helps people manage negative feedback. So overall, all of those things are like, so this literature argues that overconfidence actually helps people with their everyday lives, in particular helps people maintain a good mental health. And there's sort of this a term called depressive realism, which is to say that realistic expectation might actually be detrimental to mental health. So that the world is just difficult in various ways, and bad things are happening in many lives. And if people are not overly optimistic about what's going to happen in the future and so on, that might be actually bad for their mental health. We'll return to this issue on happiness and mental health in a later lecture, but I wanted to sort of flag these things are very much like linked to each other. And another sort of reason perhaps why over-optimism might be in fact good or like not detrimental is because not only makes people happier, but it might also help people protect their mental health. Okay, so then just very briefly, and this is sort of more like there's some research on some of those things, some of this is more anecdotal. What are some factors that affect the extent of positive biases? So people tend to have greater biases, in fact, with respect to prospects and traits that are personally important to them. On the one hand, you might say, well, people should also be better informed about those things. But to the extent that it affects their utility, they might be more biased, right? If it's stuff that's really important to you, you might be more biased because that's precisely what's going to make you happier. Available or imminent objective information tends to decrease biases, as in like, and this is kind of what I was talking about with MIT students, when you think about sort of academic performance, you get lots and lots of feedback every single semester. So in a way, it's more difficult to be overly optimistic or to maintain an overly optimistic picture of your academic self if you get all these objective signals over and over again. So one prediction here would be that, for example, if you looked at first, second, third, and fourth year students, that perhaps some of the underconfidence only comes later in the semester. Of course, there's other reasons why that might not be the case. Then if feedback about the prospect or any prospect is more ambiguous and subject to interpretation, biases tend to be greater. So people are particularly biased in situations where people get ambiguous feedback where like you can interpret things either way. So, either you were like really smart and did something really great, or you're just lucky. And people tend to, in many things in life, people tend to interpret sort of lucky things that happened in their lives, tend to think that those are due to skills. There's this very nice work and book by Robert Frank. He's at Cornell University, who sort of argues that people tend to interpret a lot of things that happen in their lives that really are just mostly luck. They tend to think that it's due to their amazing abilities and so on. And sort of, and that's the reason for that often is that a lot of this feedback or like a lot of this information is ambiguous. You can interpret it either way. And people like to think that good things are because they did really great, and bad things are because they just happen to be unlucky. If people, and that's quite interesting, if people feel like they have control over the outcomes, biases tend to be greater. Expertise sometimes increases biases, but not for experts who get very good feedback. So meteorologists or the like, who get like lots of feedback all the time, they actually tend to not be overconfident because, again, like if you get so much feedback all the time, it's hard to sort of maintain your over-optimism. Okay, so now one question you might sort of have is, well, I showed you a bunch of data information on bias beliefs, but not a lot in actual action. Of course, the testing behavior and the Huntington's disease and so on are some actions, but a lot of the stuff on the Weinstein and other studies were just about self-reported beliefs. And one question you might have is, well, this is about self-reports. What about like real preference on choices that people make? So there's some evidence that's from lab experiments, and there's some other evidence that I'll show you that are sort of about actual choices. So one very nice experiment is the paper by Eel and Rao from 2010. The way this works is people are given feedback about, so people do an IQ test and they're rated according to their physical attractiveness by others. and in the study, and they get feedback about sort of this IQ test score and their physical attractiveness. These two things are chosen presumably because people care a lot about them. People care about how smart they are. People also care about how good looking they are. And then, so in the study, the authors elicit people's prior beliefs, the beliefs at the beginning before they receive information, about a rank between 1 and 10. So people are put in groups of 10, and they sort of ask about, like, in a group of 10 people, how do you think you rank compared to others? And then people get some information, and they get, in particular, bilateral comparisons with another participant in the group. And then the authors solicit their posterior beliefs after receiving this information, and also the willingness to pay for true ranks. And broadly speaking, what the authors find is there's asymmetric processing of objective information about the self, in particular when people receive positive news. So when somebody says you've been compared to another person in the study, and you're like better looking, or like you have a better IQ score than this other person, people tend to be roughly Bayesian, as in like they tend to be like pretty good at actually sort of updating based on that information. In contrast, when people receive unfavorable news, they tend to essentially discount the signals, and they tend to essentially not really react to that information. So that's very much consistent with people who are very happy to receive positive feedback, and they're actually good at sort of integrating it, as in like they're good at sort of doing the math as a Bayesian would want them to. But once they get negative feedback, they essentially mostly discount that information, presumably and very much consistently with motivated beliefs. People tend to want to have positive images of themselves. There's also some evidence of people's willingness to pay for information if they think the information will be good, and not willing to pay for information if they think the information will be bad, so if they're low in their ranks. Again, people want to hear good things about themselves, and they learn more, or they're willing to learn more when they receive positive news. They're also willing to pay more for information that they think will be positive. There's some other evidence that's similar to that. There's a very nice similar paper by Mobius et al. That's very similar to Elon Rao. There's some very nice work by Florian Zimmermann on motivated memory. So that paper argues that it's not just about when people update immediately. So when people are given positive or negative information, they update differently. But what Florian Zimmermann shows is that in his work, that when people are given this information, in fact, in his experiment, there's no asymmetric updating in the short run. So when people are given this information this is about like how they did in a test in Germany, in the short run, people seem to actually be not overly optimistic in their updating. But then a month later, when the author goes back to people and asks them about the information that they have received and their beliefs, people tend to remember positive signals more than negative signals. And that sort of suggests that memory can play an important role in the formation of motivated beliefs. When stuff happens, good stuff, people remember more, and bad things, not so much. Now, those are all kind of like lab types experiments where people are incentivized to give correct answers, but in a way it's sort of somewhat contrived. There's also quite a bit of evidence in the real world setting, in particular when it comes to like finance or trading behavior. For example, there's Barber and Odian that shows that, looks at overconfident small scale investors. Men, for example, tend to trade a lot more than women. We also know from other settings that men tend to be more overconfident than women. Those men then also lose more money or make less money, plausibly due to overconfidence. With this type of evidence, it's often a little tricky because it's hard to say, is it due to gender, is it due to overconfidence, or maybe other things that are correlated with this. But there's quite a bit of evidence on that kind of behavior, that essentially overconfidence leads to worse decision, here in this case, trading decisions. There's also a very nice paper by Ulrike Malmengren and Tate on managerial hubris. They have a clever way of identifying overconfident managers, which essentially is managers that are overconfident. They are holding stock options of their own stocks. So you're not supposed to do that. And you will most likely do that only if you think, your company is going to do really great compared to other companies. Instead, you should exercise your stock options and sort of diversify, and not sort of be overly invested in your own firm. But if you sort of think that you're really great, or your firm is really great, you might not want to do that. And precisely those overconfident managers engage their businesses in more mergers, and those mergers, in the end, sort of show in fact are not good. People tend to do too many mergers that sort of essentially destroy value, presumably due to overconfidence. So there's that kind of evidence as well. So overall, we sort of think there's quite a bit of evidence of people systematically holding over-optimistic beliefs, and those over-optimistic beliefs are affecting people's choices in a way that makes them worse off in some ways, in particular in sort of finance choices where people tend to lose or destroy value. Okay, any questions on this before I move on to heuristics and biases? Okay, so then we talked about 3 of our 4 issues here already. The last thing that we haven't talked about very much is to say Bayesian learning is just really hard, and people might just not be good at it, not for any motivated reasons or because of any utility reasons of like anticipatory or ego utility, but it just might be really hard to do when people essentially use like heuristics because it's too hard to compute these things on their own. Now, we talked about this already quite a bit, sort of lots of economic choices are made under uncertainty. Almost anything in life involves some uncertainty. So we need to kind of know something about the likelihood of relevant events. And sort of, if you decide which topic in the course to focus on when you study for an exam and you only have like one night to do so, if a basketball coach decides whether to leave tired players on the game, you kind of make some probabilistic judgment about like which player is going to be best. Many medical, managerial, educational, career decisions, essentially all those kinds of decisions are involving probabilities of there's some probability of good things happening, some probabilities of bad things happen, and you need to make some estimates about those probabilities. Now, how to make individuals probabilistic judgment of this kind? So far, when we talked about risk preferences early in the semester, we essentially looked at like how do people make these choices for given probabilities, right? That was essentially prospect theory. That was about Kahneman and Tversky in 1979, which was, how do people think about risk? And what we always assumed was that the probability distribution was like given. There's a 50% chance of something good happening, 50% chance of something bad happening. And now how do people make those kinds of choices? What does their utility function look like? Now we're going to talk about like how do people learn about such probabilities? How, in the first place, do they update what probabilities are like, which is, of course, a very important input in their decision making. Now, and then this is sort of based on pioneering work by Kahneman and Tversky, even earlier than the 79 paper. This is in particular a paper on 1974, which is in the reading list and on the course website. Now, first, I want to start with, and this is, I think, important in behavioral economics, to sort of acknowledge and trying to sort of emphasize, people are pretty rational and pretty good in various ways, in the sense of people get lots of things right. In particular, people are pretty good in terms of like broad directions of people's probability judgments. Here's some very simple example. Imagine you're deciding whether to see the new James Cameron movie. This could be a James Cameron movie. It could be a Korean drama or anything else. People think about like they want to watch something new. Well, how are you going to do that? Well, you can read some online reviews. You hear some opinions from your friends. You look up some Rotten Tomato or other ratings, and then you sort of try to make those kinds of choices. And so you start maybe probably with like, okay, have I seen like a James Cameron movie before, or is that Korean drama or whatever you're interested in? Have I seen something like this before? How much did I like the previous one? That could be like your prior that you start with, and then you get these other pieces of information of online reviews, various opinions from friends, or Rotten Tomato ratings, and how do you use those then? What do you do with those? So essentially what you're going to do is you have some prior, which is about about James Cameron movies or whatever to start with, and that's kind of like that's what you use to start with in the first place. And then you get essentially these pieces of information, and if there's sort of positive pieces of information about those specific movies, then you're going to update up, and if they're bad, if your friends don't like it, as you said, they update down. Notice that it could also be that you have a friend who has like terrible taste in movies, and if that friend does not like a movie, that you sort of update the other way and so on. So it doesn't need to be that like your friend's movie ratings are positively correlated with yours. That could still be informative. If somebody has terrible movie taste and likes something, that could be actually good news for the particular movie. But exactly, this is what I have here. Essentially, what you're going to do is a version of this would be you start with like your base rate or your prior, and then essentially you use the various pieces of information and then sort of adjust your probability up or down. Suppose you have to sort of your willingness to pay or your probability of seeing the movie or doing other things, or your probability of liking the movie. You adjust it up or down based on the different pieces of information that we get. And so generally people are pretty, and this is a pretty reasonable and sort of mathematically well-founded procedure. This is actually pretty close to what a Bayesian would do. So people are actually pretty good at this. You know, they understand sort of the basics of forming likelihood estimates. They know the direction in which features of baseline likelihood and available information should affect estimates. So overall, people are pretty good. Now, what's much harder to do is not just the direction, but also the extent to which you should update. That is to say, people know kind of which direction to move, as in like, if you and I like the similar movies and I tell you this movie was great, it's pretty clear that you should move upwards. What's much harder to understand is like, by how much should you move upwards in your estimate of how good the movie or the probability that you like the movie is. And so, and that's true for many things in life. People are pretty good at the direction in terms of like where to move up or down. What they're much worse at is, you know, how far to adjust their estimates. And that's, you know, where they should be using Bayes' rule, but that's extremely cognitively demanding. And so in many situations, people tend to not get that right. Now, just to sort of remind you, and I think in recitation you discussed this as well, what is Bayes' rule, or how does Bayes' rule work? Let me just go very quickly through that and then focus on the next evidence. Here's one example. Suppose you have a coin that you start off thinking as is fair with probability 2/3. That means like the coin is biased towards heads, or the coin is like heads and tails. It's biased towards heads with probability 1/3, in which case heads comes up 75% of the time. Now, if you flip the coin and it comes up H heads, what's the probability of that that it's fair? Clearly, it should be like sort of 2/3, because you know you got like some signal. But by how much should you adjust is actually very hard to do. So you can think about this in your head, and then you'll realize it's actually kind of hard to do unless you can actually write it down. So suppose you had to make a very quick decision in particular. It's actually very hard to do this quickly on your own. You can do this particularly with one signal, but suppose you get like several signals, it gets much harder and harder over time. Now, how would you do this? You can sort of, in this particular case, you can just do a graphical illustration. Again, I'll do this very quickly, but you can read about it overall. You can think about there's sort of two types of coins, or like urns. There's a fair coin that's like represented by an urn with equal number of heads and tail balls. And there's an unfair coin, which is represented by an urn in which 75% of the balls are H. So you don't know whether the coin is fair, so you don't know which urn you're drawing from. And one way to think about this is, imagine you're drawing from an urn that contains both of those urns. Of course, you need to sort of then also take into account the probability of the fair ball being 2/3. So the fair urn has like twice as many balls as the unfair one. So you can sort of represent it in that way. And then suppose you draw a ball randomly and it's H, what's the probability that it came from the fair urn? And again, if you've taken sort of probability classes and so on, that should be relatively simple for you to calculate. But here in the graphical way, you can look this very simple. There's essentially 7 red balls. There's 4 in the fair coin and 3 in the unfair coin. So the probability that came from the fair coin is 4/7. Similarly, if you draw like a T, then the probability came from the fair urn is 4/5, right? And that's in some sense, you can write down the math and it's pretty clear and so on, but in a way that it's hard to do this in your head in the sense that it should be lower than 2/3, but like how much lower and how much should you adjust is actually kind of hard. And here the answer happens to be 4/7. And so here's then the sort of the formal way of doing this. I'm not going to go into this, but trust me, the answer is 4/7. Now, even this simple example of Bayes' rule, maybe it was very simple for you, but it's somewhat difficult to follow in the sense of like, would you have gotten the 4/7 right immediately if I gave you 10 seconds? Maybe, maybe not, but probably quite a few of you would have gotten it wrong. Now, in addition, then, if you try to apply these kinds of rules or the Bayes rule in new situations with multiple pieces of different information is far more difficult. Suppose I told you you'd draw like 17 times and you get those signals, and without replacement or with replacement and so on, things would get way, way more difficult. And the earn example is in fact a much easier one because there, at least I'm telling you exactly what the probabilities are. But in many real world situations, you don't even know that. A friend telling you the movie is good or bad, it's not clear how to read that signal, how do you think about that signal as a whole. So, but most people don't know the precise rule of Bayes' rule. I guess at MIT, most students do, but in the general population, people don't. And even if they do, they can't or don't want to think so hard in many cases. So what people do instead, they use intuitive shortcuts to make judgments of likelihoods. Now, that's a good thing. So like we want people to use these shortcuts because otherwise they will just freeze and not be able to make any choices. So in some sense, it's good that people are sort of simplifying problems and they make some choices quickly. So that's in some sense, it's good, but it also leads to systematic mistakes, right? Because in some sense, you can do shortcuts and they help you to get things like approximately right. But now if we can sort of understand their shortcuts, then you can also understand their systematic mistakes. So so what people tend to do is they focus on one or like a small set of the situation at hand that seems most relevant. They focus on that to make their decision, and often then they sort of they systematically neglect other more complicated or other issues of the situation, which makes their the likelihood of their estimates typically incorrect. And now the question is, can we sort of understand what people focus on, and can we understand what causes these systematic biases to sort of make clear predictions on how people do things wrongly? And then perhaps if you want to help people make better choices, we can provide them with relevant information as well. Now, one particularly interesting issue is sequences of random outcomes. So as I just showed you, if you sort of draw balls from an urn, that's a very relevant situation, not because people in the real world, in real world situations, draw balls from urns, but rather because in many situations, you do actually get repeated signals over time that you should use to update. So an investor might observe past performance of mutual funds before deciding which one to invest in. A patient or doctor might observe the outcome of prior surgeries before deciding whether to undertake the surgery or which doctor to choose. A coach can observe the recent performance of a basketball player before deciding whether to put the player in the game. So there's lots of kinds of situations where people get repeated signals over time and then have to sort of try to infer likelihoods or probabilities of certain events to happen. So that's a very common thing in the world that we should try and understand. Now, one systematic pattern that we see in the world is what's called the gambler's fallacy. That's the false belief that in a sequence of independent draws from a distribution, an outcome that hasn't occurred for a while is more likely to come up on the next draw. So the important part, he was doing a lot of work here, is independent draws. Suppose there's a distribution of outcomes and there's independent draws, which means that essentially what matters in what happened in the last 2, 3, or 4 draws should not have any effect on what's going to happen in the next draw, right? So if you play roulette or any sort of like poker or the like, if you get like red several times in a row, that has exactly no impact on like how likely it is that red or black is coming up in the next draw. But people tend to have to this almost like folk knowledge of, well, if red came up a few times, now black is due, and the other way around. And that's true in many different situations but the important part here is that there's a sequence of independent draws. So as in to say, these are situations where the probability distribution is actually known. That is to say, when you play roulette or like you go to a casino, it's not like you need to like learn about what's the probability that the roulette is like fair or not. You know that like there's some monitoring and so on in those situations. You know essentially that the chance of getting red or black is like the same, and yet people tend to make these kinds of updates. There's a nice paper by Gould and Hester, an old paper that sort of shows this quite nicely, in which subjects are told the coin with a black and a red side would be flipped 25 times. And the experiments are slightly sneaky here because essentially they reported people a predetermined sequence of events. So there's some deception involved here, which is a little bit trickier, but it's mostly fine. So what they see is essentially the subject sees 17 mixed coin flips. So you see a sequence of coin flips. It's red and black and so on. And then at the end of it, you see essentially one black and four reds. And so again, this is supposed to be like independent draws, which would, to make this case, in this experiment, they sort of rigged the last five draws, which is not quite ideal, but let's just go with this for a bit. And so what essentially people see in this experiment is mostly evidence of red and black, where roughly red and black is even. If anything, so the 17 are mixed, these are actual draws. If anything, people saw more red than they saw black. Then on the 23rd flip, after seeing these 22 flips to start with, the participants were given a choice between 70 points for sure or 100 points if the next flip was their color. And points are essentially stuff they can get money for eventually. And so now it's randomly chosen whether half of the subject's color was red and half of them was black. And so now the propensity to take the 70 points reveals the beliefs about the odds that the next flip would be their color. So if you think the probability is 50%, which is kind of like given the information that you got, you should probably roughly think it's 50%. Then, and if you're risk averse in particular, you should surely choose the 70 points for sure, because an expectation, if it's you get p times 100, if it's 50%, you get like essentially 50, right? So you're only going to choose the 100 points if the next flip is your color. Well, if you really think your color is likely to occur, in particular if your probability of that occurring is like 70% or higher, notice that even assumes like risk neutrality, right? So if people are risk neutral, if they think the probability is 70%, they should be indifferent. And again, if they're risk neutral, if they choose number 2 here, their color, well, that's only the case if they think the probability of the color occurring is higher than 70%. Okay? And sort of given that the evidence that they saw, it's going to be rarely the case that, or people should really, given the evidence that's there, the best thing they can do is essentially, or the thing is set up such that they really should choose number 1. But of course, if people think that, or the idea is here, if people think that there was 4 times red, so now black is due, the prediction would be that people will be more likely or will choose item number 2 if their color is black. Okay, and so 24 of 29 red subjects chose to take the sure thing, which essentially is option 1 here that I showed you. And 8 of 30 of the black subjects did. So these are essentially the people who choose their color. So if people have black as their color, they essentially choose this option because they really think like now black is due because there's been like essentially 4 reds in a row. Now again, if you're told, and that's a little bit unclear in this experiment about like these being independent events, which for coin flips really they should be independent events, that doesn't make any sense. You should, if anything, think red is more likely because the coin might be sort of more likely to be red. But sort of thinking that black is more likely surely is not a good idea, and it will essentially make you lose money. Now, there's some interesting variant of this is for which they said for some variants, the 23rd coin flip was delayed by some time, 24 minutes. And what they then find is, in fact, weaker evidence of what's called the gambler's fallacy, which seems to sort of say that, like, once you let the coin rest for a while, people seem to think that like letting the coin rest for a while would sort of makes it more likely, I guess, that the streak continues, or less likely that essentially black null is the case. So people seem to have sort of these fairly, and I think that's fair to say, rational beliefs about, or biased beliefs about what's going to happen next, and that seems to like be easily swayed by even similar, relatively small things. It's like the coin needs to sort of revert, but if you wait for 24 minutes, not so much anymore. There's quite a bit of work on the gambler's fallacy overall in various settings. That's just one setting to illustrate this. There's quite a bit of other work in that area, and it's a fairly robust finding that people found in the literature. Now, a second pattern that people find is what's called the hot hand fallacy. That's the idea that, in particular, basketball fans or other sort of types of sports fans, players, coaches, believe that there's systematic day-to-day variation in players' shooting performance. Again, that's for basketball, but it's also true for other sports. So the performance of a player, the idea is that the performance of a player may sometimes be predictably better than expected on the basis of the player's overall record. And sort of what people would say is like, well, the player is on fire today, or is a streak shooter, and so on. And sort of the idea here is that on fire today means that he or she is more likely to hit his or her shots than on other days. So that's to say, the prediction here is that made shots should cluster together. Like on one day, you happen to be really good, or maybe in the first half or second half, and conditional on having made a few shots, the next shot should be much more likely than sort of the unconditional probability. There's lots of work on this issue, starting by Gilovich and Bologna and Chorsky in 1985. People have gone back and forth between saying, like, in fact, there is sort of such a thing as a hot hand or not. The initial claims were essentially there's no such thing. People believe that there's a hot hand going on, and like players are really sort of running hot, but in fact, they're not. Some other evidence later showed maybe there is actually such a thing, that it was contradicted again. So it's kind of complicated, but overall it seems to be that people tend to be, like players, fans, and so on, tend to be quite over-optimistic about the hot hand and streaks happening in reality. Now, one question is that seems kind of like odd in some ways. And so on the one hand, it seems like there sort of seem to be the hot hand fallacy and the gambler's fallacy seem to be opposites of each other. That is to say, the gambler's fallacy is the belief that the next outcome is likely to be different from the previous ones. Right? I showed you, like, if I show you, like, if you're gambling, you get like 4 reds, now you say it's going to be black next. Or if you have like 3 heads, that you think your coin is going to show some tails. That's essentially saying, like, you saw a bunch of like outcomes of one kind, the next one will likely be different. On the other hand, the hot hand fallacy is sort of saying, like, well, it's the belief that the next outcome is likely to be similar to the previous ones. Now, what's going on here, you can think of both of these as a consequence of what's called the belief in the law of small numbers. Now, what is that? You should all know the law of large numbers, which is in large samples of independent draws from a distribution, the proportion of different outcomes closely reflects the underlying probability. So essentially, once you have sufficiently many draws from some distribution, the distribution will converge to like what you're drawing from. Now, what's the belief in the law of small numbers? Well, it's the belief that in small samples, the proportion of different outcomes should reflect their underlying probabilities. So usually the law of large numbers, it's called the law of large numbers because you need a large number of draws. That's why it's called that way. But people seem to think that the law of large numbers also applies to small samples. And so how does it explain our puzzle? Well, then there's a question of, like, does the person know the underlying distribution? So if you think you know the underlying distribution, for example, if you think you know for sure that the coin is fair, or like the roulette table is not cheating you, you might sort of say, well, roughly I should see as many reds as I should see blacks, or I should see as many heads as I should see tails. And so now if I have a sample of like 4 draws, if I already have like 4 heads, then I might sort of think in that small sample, I need to see essentially a roughly equal fraction of like heads and tails. And therefore, if I've seen 4 reds, the next one is due to be black. And of course, that's not true, because essentially the law of large number does not apply to small samples, because it's called the law of large number and not the law of small numbers. But mistakenly, people seem to think the law of small number applies. In contrast, if the person does not know the distribution, the belief in the law of small numbers can lead to the hot hand fallacy. That's to say, if you're trying to learn about the distribution of shots, or like the underlying probability, if you see some good events in a row, if you see like 3 heads or 3 tails and so on, if you see like a player making 3 shots in a row, you might sort of try to infer, oh, today's a good day or a bad day. And people tend to over-infer. They tend to think like they can learn more from these 3 shots than they actually do. Really, to be able to estimate whether a player is running hot on a given day, you need quite a few draws. But people think like if a player makes 3 shots, that already means that like his probability of making good shots on that day are way higher than it actually is. So essentially, people mistakenly seem to over-infer from a small number of observations what the underlying probability distribution is. And in that sense, the belief in the law of small numbers can lead to the hot hand fallacy as well. So these are essentially sort of 2 very different conclusions that seem to come from the same underlying issue. Then the last issue pattern I'm going to show you, by the way, there's more patterns such as those, but I'm sort of just showing you 3 of them to sort of give you a sense of what's going on. Remember the example that I showed you in the first lecture, which was a question about like base rates or base rate neglect, which is the question about like 1 in 100 people have HIV. We have a test that is 99% accurate. If a person tests positive, what's the probability of having the disease? And so I showed you this before. The true answer is 50%, but quite a few of you answered 90%, 99%. And sort of a plausible explanation is that people probably forgot to take into account how few people in the population have the disease to start with. And so this is what's called the base rate neglect. When people are given some new information, people tend to, or in this case, I guess the test of like 99% being 99% accurate, people tend to focus on that piece of information. They tend to neglect the underlying base rate, which in this case is like 1 in 100 people tend to have the disease to start with. And again, that's sort of a natural consequence of focusing too much on like one central aspect of hand, which is the 99% accuracy of the test. In a way, that's again can be useful, but it's sort of systematically getting people to make wrong choices. And there's quite a bit of evidence showing this in the literature. And sort of here's again what you should be doing, and sort of here's the probability of this is trust me that this really is 50%. Now, the last piece here is in terms of like biases or systematically biases. What I showed you so far was, well, people have a hard time making right choices even in simple informational environments. Now, 2-dimensional learning is even more complicated. And what I mean by 2-dimensional is to say, well, if you try to learn about news or like the accuracy of news, if you watch news online or anywhere else, you don't need to only like learn about like somebody gives you some information and you try to sort of update based on that information, but rather you also need to learn at the same time about the accuracy of the piece of information that's given to you. That is to say, if you watch something online, any article, not only you need to sort of understand kind of like what to learn from that information, that piece of information, but you also need to sort of understand the underlying source of it. There's quite a bit of work recently on fake news and sort of the question on like, can people in fact detect fake news? Does it have to do with like partisanship in particular? So you might think that Republicans or Democrats want certain news to be true. So you might sort of think that like Republicans are more likely to want to believe news that are biased towards Republicans. Democrats are more likely to believe news that are more likely to be Democrats, and sort of therefore they might be more likely to trust fake news or fall for fake news. David Rand, in fact, seems like it has actually, or at least in their work, it seems to have, and by the way, he's at MIT in the marketing department, or at Sloan in marketing, in the marketing group, he seems to find that it's less about partisanship, but rather about people being not paying attention and being somewhat lazy in making their choices. And then, like, once you draw their attention to, like, here's an article that might be fake, people might seem to be actually quite good at learning about the accuracy of it. Now, let me sort of just summarize for a bit and then see whether there's any questions. So what I've shown you is essentially using Bayes' rule is difficult, or give you some sense of it. I showed you like 3 systematic deviations from Bayesian updating, which is the gambler's fallacy, the hot hand fallacy, and base rate neglect. These are all well-known deviations from Bayesian learning. Now, 1 and 2, I've argued, can be explained by the belief in the law of small numbers. And there are really important real-world implications of those types of outcomes. For example, one very nice recent paper, Maddie talked about it a little bit in recitation, but only very briefly, is this paper by Kelly Shu and co-authors about decision-making by judges, umpires, and loan officers, where essentially if you're a judge or loan officer, you see a bunch of applications over time, and judges seem to essentially engage in what's the gambler's fallacy. That's to say, like, if they see 3 applicants in a row that happen to be very good or very bad, that tends to affect the following applicant. That is to say, judges, when they decide about parole and so on, if they have given parole several times in a row, they might think, you know, the next person who's in line, if they've granted parole several times in a row, the next person then would be less likely to get parole, even though, of course, these are independent events. It just happens to be that one person happens to be after or before certain applicants in a random way. So there's really sort of important decisions that the gambler's fallacy might affect. And more recently, when you think about base rate neglect, in some sense, the example that I showed you seems to be like a fairly academic example in some ways. But when you think about, like, and I don't want to talk too much about COVID-19 since you see that in your life too much already anyway. But if you think about, like, tests for COVID-19, there's now talk about antibody tests, and particularly as tests that seem to be highly informative. In some sense, there's sensitivity and specificity, meaning like their type and 2 errors are pretty low, or their sensitivity and specificity is very high. These tests tend to be highly accurate. But in fact, how much you can learn from those tests is actually very limited if the overall fraction of people who are infected is not that high. And that's exactly the example that I just showed you. If the fraction of people who are positive in the overall population is relatively low, you're doing a test and essentially receiving a negative signal actually is not giving you a lot of information overall. And this is precisely, people tend to miss that fact precisely because of base rate neglect. Let me stop here for a second. That was all a little bit fast, so let me see if there's any comments or questions. Right. So then let me, in the last 10 minutes, talk a little bit about heuristics and biases. And this is what Kahneman and Tversky really are very well known for. So the way to think about then biases and probabilistic judgments, just is what we already discussed. The starting point is that applying the laws of probability and statistics is often impossibly hard. So people use their quick and intuitive judgments to make likelihood estimates. And so there's a seminal work by Kahneman and Tversky and lots of subsequent work that sort of tries to like think about these biases. If you're interested in learning more about this, is Thinking Fast and Slow by Danny Kahneman. Danny Kahneman is really sort of a terrific book about thinking about this. Now, what's a heuristic? It's an informal algorithm that generates an approximate answer to a problem quickly. And therefore, because it's sort of like informal, it's kind of hard to model. Well, the previous things that I showed you, so I showed you before, let me just go back for a second, the gambler's fallacy, hot hand fallacy, and base rate neglect. Here you can sort of do reasonably, you can sort of like write down models that capture these phenomena pretty well. Right, you could, for example, for the base rate neglect, you could just have a parameter as like how much weight do people put in the base rate, how much people how much weight do people put in like the new information that they get. And then that parameter will essentially sort of, you can estimate that parameter and you can write down a model that's not Bayesian, but sort of close to Bayesian. Similarly, for the hot hand fallacy and gambler's fallacy, you can sort of model that people essentially apply the law of small numbers. And again, that's a model you can write down and estimate. In contrast, some of the stuff that I'm going to show you next is it's much more difficult to model because in some sense, some basic laws of probability do just not apply anymore in the sense of people don't respect them anymore when they make their belief updating. Let me show you in a second what I mean by that. But again, heuristics have a good and a bad side. So they speed up and make possible cognition. So they help you make decisions in your everyday lives. And without heuristics, it would be really hard to make any decisions overall. But because they're shortcuts, they occasionally produce incorrect answers or biases. So these are essentially unintended side effects of sort of adaptive processes. And that makes it very useful to study heuristics and biases together. In the same way as you would study vision and optical illusion together, studying them jointly is very helpful because they're sort of the product or the result of the same thing. Things are hard, therefore they use heuristics, and because they use heuristics, that leads to systematic biases. Okay, so now I'm going to show you like a few of those heuristics just to give you a sense of what these are. One of the most well-known ones is what's called the representativeness heuristic, which is about Linda. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and has also participated in anti-nuclear demonstrations. The question comes then, rank the following statements from most to least probable. And so here's the statements. You can read about them, all sorts of different things. In particular, what Kahneman and Tversky are focusing on is items 6 and 8. And item 6 is Linda as a bank teller, and item 8 is Linda as a bank teller and is active in the feminist movement. Now, one thing that should be clear is that like 6 is more likely than 8 because essentially 8 is sort of conditioning on 2 statements while 6 is only conditioning on 1. So like if Linda is number 8, she of course, it's implied that if she's a bank teller and something else, of course, then she also is a bank teller. So it should always be the case that 6 is more likely than 8. But what people tend to do quite consistently is that, in fact, people rank it more likely that Linda is both a bank teller and a feminist than that she's a bank teller. And there's quite a bit of work on this, and they sort of showed this in various ways. But essentially, it's what's called the violation of the conjunction rule, which is sort of a very basic law of probability. And precisely because it's such a basic law of probability, it's hard to actually model this because essentially you can't use simple things that should be true in probability theory. There's some potential concerns about this, people misunderstanding this, but there's sort of subsequent experiments that essentially show that that's not the case. Now, what's going on here is what's Kahneman and Tversky called the representativeness heuristic, which people essentially use similarity or representativeness as a proxy for probabilistic thinking. So based on the available information, people form a mental image of what Linda might be like, and then ask them, what is she, about how likely is that, for example, she's a school teacher, they might ask them how similar is my picture of Linda to that of the school teacher. And so then turn this similarity judgment into probability judgment. So here, of course, the example was very much like rigged in the sense of like, they're asking things about like discrimination, social justice, and anti-nuclear demonstration and so on, which made people think like, well, that's a person that's likely be part of the feminist movement. And then people focus on that when making these choices. And they forget the fact that like essentially 6 must be by sort of definition more likely than 8. So that's a common thing that people use. There's quite a bit of evidence of that. And again, that's a very reasonable heuristic, and it probably works in many cases, but it also leads to very predictably bad choices, and it's a poor predictor of true probability in several situations. Similarly, sort of what's called the availability heuristic, people assess the probability of an event by ease of which instances occurrences can be brought to mind. So when you ask people, for example, about are there more suicides or homicides in the US each year, people will think about suicides and homicides that they can recall. They might think about like what they watched in TV and so on, and they judge the frequency of each based on how many instances they can recall. And people will be much more likely to recall homicides because they are much more salient in the world, and that leads to people to think that murders are way more common, which in fact is not the case. Again, it's a very sensible heuristic that people use. More often than not, it's easier to recall things that are more common or probable. So, that's reasonable overall, but again, there's sort of predictably things that are then more salient, that get more attention, people tend to think they're much more likely than they in fact are. Let me skip the familiarity and anchoring adjustment and just sort of like conclude. So what have we learned about beliefs overall? So we studied several reasons why people might miss information and fail to learn. We talked about attention. Attention is limited, and therefore they might miss things. We talked about like why might they miss important things? Well, because they might have wrong theories of the world. Then we discussed people might derive utility from wrong beliefs and therefore might actually not want to learn or might be systematically engaged in like trying to deceive themselves. And then we talked about people who might be bad at Bayesian learning. Now, what's important here, I want you to take away, it's important to understand these underlying reasons why people are misinformed, because they might lead to vastly different policy implications. For example, if you were to make information salient, makes sense if people think, if you think people miss information and important things in the world. So if you, for example, think that people just might not be aware of the fact that certain foods have more calories than others, then making like that information very salient to people when they purchase things, drawing their attention to that stuff could be really important. It could be really powerful in helping people make better choices, right? Or if they think just they have like wrong theories of the world, if they think, calories are not that important, or if they miss the fact that smoking causes cancer, well, you should really sort of draw their attention to them and help them understand it. And that's kind of what a lot of labeling and a lot of sort of making things salient often is about. Now, but if people don't want to learn, if people actually have motivated beliefs in certain ways, and in fact, they know that in some ways, deep down inside, they know that the relevant information already. Smokers, for example, might know exactly that smoking is bad for their health. So providing them with information about smoking will not actually make them learn. Or like if you wanted to give somebody information about like how to best take care of your health when it comes to Huntington's, well, that's not helpful if the person doesn't actually want to believe that they have Huntington's, if they're never even going to read what you send them, if they want to maintain their positive image about their positive beliefs about their health. And in fact, when people derive utility from beliefs, correcting those beliefs can make them worse off, right? If somebody wants to believe that they know kind of like the probability of having Huntington's is reasonably high, but they want to maintain the beliefs that they're healthy and they want to be happy for the next 10 or 20 years. And then maybe at some point the disease will break out, but their choice is they want to be think that they're healthy, and they do not want to adjust their behavior. So who are we then to tell them otherwise? That's their choice. If it makes them like less happy, we might actually make them worse off. So in some ways, there's at least some arguments for respecting people's choices if they want to be deluded, if they want to delude themselves, and the consequences are not severe in the sense of if these are situations where they can't really do much about, then in fact, leaving people uninformed might be the right thing to do. And then sort of understanding systematic biases based on heuristics can help improve decisions. That's in some sense a lot less controversial if you think that people are systematically making wrong choices because they learned sort of wrongly and they just have like wrong information in their heads. Sort of providing them with the correct information seems like unambiguously something one should do. That's all I have on beliefs for you. Next time we're going to talk about projection and attribution bias, but I'm also happy to answer any questions in the next few minutes if you have on this lecture or on the summary that I just showed you.